Hey guys, this is Professor Janacek, and I want to talk about extrema and saddle points for functions in several variables. Now when I talk about extrema, we're going to look mainly at relative or local extrema, and that means either a relative minima or relative maxima. Of course, you probably know what these ideas are. Relative minima are going to be the low points. They are the points in the domain where the function is at its lowest value. Relative maxima are points in the domain where the function is at its highest. And saddle points actually are interesting. They are points in which you have both things larger and smaller than that function value. So it's going to have both things above and below, as you can see here. The idea is that it looks kind of like a saddle. All right, so in order to determine these, first off, we will need to find critical points. A critical point is a point in the domain such that either the first partial with respect to x or the second partial with respect to y, both evaluated at the point AB, is equal to 0, or the first partial with respect to x or the first partial with respect to y, those does not exist. That's going to be a critical point, and it turns out as we can see here, the first derivatives give us where the critical points are, and the second partial derivatives, those are going to classify these points. So we have what's called the second derivative test in order to determine these extrema and saddle points. Notice a saddle point is not an extrema, but we often talk about those collectively. So we'll start with the critical point, and then we take the second partial derivatives. Those second partial derivatives do need to be continuous on the open disk around that point. And then we're going to take this d. So d of xy is f sub xx times f sub yy minus f sub xy quantity squared. What that is, just so you know, this is the discriminant. Of the matrix that's formed from those second partial derivatives, f sub xx, f sub xy, f sub yx, and f sub yy. And of course, the discriminant of that is when we multiply along the diagonals and take that difference. And it turns out that these two are the same, and so that's why we end up squaring it there. So if you remember what the discriminant of a matrix is, you can use that idea. If you don't remember what that is, you can simply take a look at this formula here. Now, how do we classify these? Well, it turns out that if that discriminant is greater than 0, again, the discriminant evaluated at the point AB is greater than 0, and f sub xx is evaluated at AB is also greater than 0, then we have a relative minimum. Now, if that discriminant is greater than 0, but f sub xx is less than 0, then what we have is a relative maximum. Right? So in both those cases, the discriminant was greater than 0. If that discriminant is less than 0, that's when we get one of those saddle points. And finally, if the discriminant is equal to 0, then that tells us nothing. This test is actually inconclusive. We would have to use other techniques. Let's take a look at an example here. Let's find all the critical points of f sub xy equal to 1/3 x cubed minus 1/3 y squared plus 3xy. All right, so what we'll need, again, we're just finding critical points, so we'll need the first partial derivative with respect to x, which is x squared plus 3y and the first partial derivative with respect to y, which is negative y squared plus 3x. And then we will let these first partials equal to 0. And simply solve this set of equations. Let's see, there are a few ways of doing it. I'm going to go ahead and take the second equation and solve for y. I'm choosing that because it has a negative, makes it a little easier. Then I can get rid of that negative. So we have x is equal to y squared over 3. Substitute that into the other equation gives us y squared over 3 quantity squared plus 3y is equal to 0. That's y to the 4th over 9 plus 3y is equal to 0. Clear that fraction, multiply both sides of the equation by 9, gives us y to the 4th plus 27y equals to 0. We can factor that. And set each factor equal to 0. And it looks like y is equal to 0. Actually, I can write this down here. Y is equal to 0 and y is equal to, that would be negative 3, right? Okay, so that tells us we have two values for y. So for y equal to 0, notice I know what x is. X is y squared over 3. So when y is 0, x is also 0. And for y equal to negative 3, x is equal to, looks like positive 3. Thus we have the points 0, 0, and 3, negative 3, and these are the critical points. And then you could use these, you can use the second derivative test to determine what happens at those critical points. I do want to point out that I am looking for just the relative extrema and the saddle points, not looking at absolute or universal extrema in this situation. All right, well, we'll have a few more examples, but hope you enjoyed.